Okay, so this video is going to be about section 5.1, which is length and dot product in Rn. This should be generally review from your Calc 3 class, but we still like to go over it, make sure we're all on the same page. We'll start with R2. If I have a vector A, B, and I want to find the length of that vector, well, the notation we use is this double absolute value sign here. That is called a norm notation. It doesn't really matter that much, but that's what we call it here. And it's just the square root of a squared plus b squared. This just comes down to the Pythagorean theorem that the length here is the square root of a squared plus b squared. If we want to move on to say R3, it's also something you should have done in multivariable calculus, and this time our vector is a, b, c. What we can do here is we actually are going to apply the Pythagorean theorem twice. So we have our vector x, and what we're going to do then is we are going to kind of draw down here, and then furthermore we can look at this here, and if you have your a, b here, then this side becomes, by Pythagorean theorem, square root of a squared plus b squared. This height here is c, and if you use Pythagorean theorem again, you get the square root of a squared plus b squared squared plus c squared, and that simplifies down to our standard formula, square root of a squared plus b squared plus c squared. So this right here is our standard formula, and it generalizes to any dimensions. So if I want to look now at Rn, and my random vector is x1, x2, up to xn, and I want to find the length of that. Now this is a vector in Rn that might be some really big size. We can't really visualize it, but you can prove by induction using Pythagorean theorem that we can just find the length by this formula here. So you just take each component, you square it, you add them all up, and you square root it, and this is how we find the length. So let's do a quick little example here. Find the length of the vector x is 1, 2, 3, 4, 5 in the vector space R5 here. And so we just go ahead and do our quick calculation. And let's see here, 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, 55 I believe. And so that would be the length of our vector. And again, you can find length of any vector in Rn this fashion. Now some things we might want to do with this here is the following here. Find a vector in the same direction as 1, 2, 3, but that is a unit vector. This is a problem that you definitely should have done in Calc 3. So what we do is we first find how long the vector x is. That's 1 plus 4 is 5, plus 9 is 14. And then once we know how long it is, we can actually divide the original vector by that length. And what that is going to mean is that now my new vector is going to have length 1. And that's what a unit vector is. Right, so the original vector x is not a unit vector, but once we divide it by its length, it is. And we can just check right here. I'll call this vector u. And if I find the length of u, it's the square root of 1 over square root of 14 squared, and 2 over square root of 14 squared, and 3 over square root of 14 squared. And then we get the following. And as you see, we get a length of 1. And again, in calculus, we really liked things with length 1 because they allowed us to specify a direction without actually like interfering with what was going on. You may recall when you were doing, say, integrals and so on, or directional derivatives, right? Remember directional derivatives? You went ahead and needed a unit vector here because you only want the size, the how big the derivative is to be based on the function. You don't want it to be based on the value of this direction here. You don't want people to have two different vectors in the same direction getting different answers, so you normalize it to where the unit vector there. And it's a very, very useful thing that we can find a unit vector in any direction using this process. And really, this is a result of the following fact, that if you take the norm of a constant times a vector, it works out to be the absolute value of the constant times the norm of the vector. And so this right here is what we're really doing up here, which is why if you divide by the length, it ends up becoming a unit vector.